Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. Today we're in AP Chemistry, Unit 3, according to College Board, Part B. So this is standards 3.7 to 3.13. Okay, and I'd already started before I realized, oh no, I need to take this. So I'll go back over that. So solutions and mixtures are 3.7, and like I was telling my class here, that most of this is easy because it's a review of honors. There's a little bit of new AP stuff, but not much. So, and the new AP stuff is fun and interesting. Okay, so what's a mixture? A mixture contains more than one type of substance. What is a solution? It's a mixture that has the same composition, color, density, and taste throughout. It's clear, but not necessarily colorless. And that's why we got a Kool-Aid man up there on the notes. Okay, so there are two types of mixtures, heterogeneous and homogeneous. Hetero, does it mean same or different? Hetero, same or different? Different, right? So the heterogeneous has differences in it. It has layers that you can see with the naked eye, and in chemistry, we call those phases. They're phases, and this is just to the naked eye. If you were microscopic, you could see differences microscopically. So our example is regular, you shake it, Italian salad dressing, versus homogeneous. So homo means same, so it's the same throughout to your naked eye, and I put may, can. Don't worry about that blank. It can be colored like Kool-Aid. So a lot of solutions are clear and colorless, but not all of them. Some of them are clear and colored. Okay, so you've got what gets dissolved and what does the dissolving, and the words are too much alike. Solute, is that what gets dissolved or what does the dissolving? It's what gets dissolved. And then so the solvent is what does the dissolving. And so how I remember this is I make my V in solvent a cup and I fill it with water. So see how I drew a big V there to fill up? Now I only have red going right now, so I guess it's got Kool-Aid in it, but it should be water. Okay, now what can be dissolved? So solid can be dissolved in liquid like sugar in sweet tea. And most of what we do in chemistry class is we dissolve solids in liquids. You can also dissolve a gas in a liquid like soda pop. So, but also, why I put fish here, fish are not a gas or a liquid, but what do fish breathe? Do they breathe the oxygen in H2O? No, they breathe O2 just like you do. It's dissolved O2. So if like your fish tank gets too hot and oxygen bubbles out of it, then you can kill your fish. Anybody ever killed your fish that way? Yes? I've killed fish many ways. That's one of them. One time my kids had aquatic frogs. Y'all ever seen those? So they have these aquatic frogs, and I got tired of cleaning their fish tank. So I put a filter in it. Well, the filter was putting too much dissolved oxygen in for frogs. It's fun for fish, but frogs don't live where water is moving real fast with lots of dissolved oxygen in it. Didn't think about it, killed the frogs. They puffed up like balloons and died. Poor little frogs. Jumpy 1 and Jumpy 2, dead. All right, I killed them. Okay, so I kill fish and frogs. Okay, so what do they breathe? O2. Now, also you can have metal dissolved in metal, and that's when you mix them while melted, and we did that when we made alloys, and we talked about that last time. Now, more about concentration. May I scroll? Everybody good? Okay. So this is a lot of facts here, but not too important for AP, so you don't have a lot here. So there are different ways of expressing concentration, but the one we do is number 5, and a little bit number 4. 1, 2, and 3, not so important, but I'm going to go over it. One way is called mass percent. It's the mass of solute divided by the mass of solvent times 100. There's another one called molality. It's got L instead, L instead of R there. And it's the moles of solute divided by kilograms of solvent, and they use that in the industry, and the symbol is little m. There's another one called normality. It's an old way with acids, and I had like never seen it before until I came here and I found this really old bottle of acetic acid in the back, and I'm like, what in the world? What is this? I had to like Google it and look it up, see what its actual regular molarity was. So in common speech, we talk about things being concentrated versus dilute, and we're actually going to use that speech in our lab that we're going to be doing. Also, and this is why I've got a little more here, more light usually passes through dilute. There's usually less particles in the solution for dilute, or there would be, not usually, but it's usually lighter in color. So we're going to do a lab using spectrophotometry based on those principles. Now, how we usually express concentration in AP chemistry is with molarity, and that's the moles of solute divided by liters of solution. The units are big M, so like this 3 big M shows you your concentration. Okay, so here's an example problem. What is the molarity of a solution that has 10 grams of sodium hydroxide dissolved in 100 milliliters of water in a volumetric flask? Well, to get this, first of all, we have to know molar mass so that we can convert grams to moles, right? So we add these up, these are off the periodic table, and we get the molar mass of sodium hydroxide is 40 grams per mole, okay? Keep it going. Okay, so our formula here is big M equals moles per liter is what we're looking for, okay, and that's what we want to solve for this. So we have 10 grams of sodium hydroxide, and we're going to set up a conversion factor. We've got 10 grams in 100 milliliters of water. So first, let's change those grams to moles. We're going to put our molar mass, 40 grams in the denominator, 1 mole in the numerator. Grams mark out. We've got moles in the numerator the way we want, but we have milliliters in the denominator, so let's change those. 1,000 milliliters equals 1 liter. Milliliters cancel out, and I'm left with moles per liter, what I'm supposed to have. So when I do my math, 10 times 1,000, divide by 100, enter, divide by 40, enter. I get 2.5 is my concentration, put it in square brackets. Okay? How do we feel about that? Yes, sir?
Where did you get 1,000 milliliters?
Just knowing it, that milli means thousandth, so there's 1,000 milliliters in a liter. Just like there's 100 centimeters in a meter, there's 10 decimeters in a meter. So that's just kind of gotta learn what those prefixes mean. Okay, here's another problem, and there's really a shortcut to this one. So there's this thing, that if you have your first concentration and your first volume, you can set it equal to the second one, and if you're missing one of these things, you just put it in this formula and you get the answer. So here's our problem. A chemist needs to produce 500 milliliters, so that's my second volume. That's what I want. Of this concentration. I want it to be 0.25 is my concentration there. And what I have is 12 molar hydrochloric acid, so that's my concentration. And I want to know how much water that I need to add to, I want to know, that's my molarity, but I want to know 500 milliliters, 250. I wrote these backwards. Molarity, volume, So what I'm looking for is what volume of this, no, I wrote it right. I wrote it backwards on here. I want to know what volume of this 12 molar hydrochloric acid do I need to pour into my flask and then add water till it's 500. Everybody see this? How much is it going to take? So all I have to do is solve for x. I do 0.25 times 500 divided by 12. And the answer is I need 10.4 milliliters of that real strong 12 molar hydrochloric acid. Okay? We all followed good there? May I scroll up? Is that good? Okay. So water is called the universal solvent because if you leave most stuff in it long enough, it can dissolve it. Okay. This next part is just a bunch of vocabulary that you learned in honors, so hopefully all you need is this little refresher. How much can dissolve at a given temperature is called the solubility. How much is dissolved is the concentration. No more can dissolve at that temperature is called saturated. We use that in common speech, don't we? More can dissolve is unsaturated. Now this is the weird one. More is dissolved than can dissolve at that temperature. This is called supersaturated. And how you do that is you saturate it at a certain temperature, and then you cool it down without bumping it, and the molecules will not get organized into crystal lattices. They'll stay liquid, and you can have more dissolved than what would normally. And if you put in a little bit of a crystal, it'll go and all crystallize, or if you bump it. And what we did a lab with hand warmers with that. Do you remember that? We gave it a little bit of energy and they went, okay. So if something can dissolve, it is said to be soluble. If something can't dissolve, it's said to be insoluble. If something can mix, it's said to be miscible. If it cannot mix, it's said to be immiscible. Now that's a lot of vocabulary words, but I bet you already knew most of them, right? A lot of those we use in common speech. So concentrated, dilute, things like that. Okay, so now we're going to do an example problem, and this is something new. Yay, we find all of that, and we're finally doing something new for AP Chem. Can I scroll this up? Did y'all get all those words? Good. All right, so mole fractions. So one of the things you can calculate is the moles of a substance in the total moles of the solution. For example, calculate the mole fraction of sucrose, sugar, where 10 grams of sucrose is dissolved in 400 grams of water. So notice it's called mole fraction, not gram fraction. So what are we going to convert to? Moles. So we're going to convert both. So we're going to convert the sugar, we're going to call it shug, and we have 10 grams of sugar, and we're going to convert the water, we're going to call it H2O, all sciencey, and we have 400 grams of water. So we're just going to do a quick little conversion. We got to look up the molar mass off the periodic table, and sucrose I have is 342.3 grams per mole. That came off of the periodic table. And this for water is 18. Y'all have probably memorized that one by now. You just add up their decimal numbers off the periodic table and multiply it by the subscripts. Okay, so for this one, somebody do that on your calculator. 10 divided by 3 42.3. Because what I got doesn't really make sense. Somebody tell me what the answer is. I might have written this down wrong. I think I did. I think I took two problems and combined them. What'd you get?
I got 0.029214.
Okay, I got 0.002, right? Or just 2?
0.02.
0.2 or 0?
02.
0.02912.
21. And then there's one.
Okay, we're gonna say that's good enough. Okay, and now do this one. Did you get 22.2? That's what I got for this one. Elisha was saying there was something off with the math with this problem last period. That's why we're taking a minute. It'd be really embarrassing to put wrong math on YouTube. I've done it before. It's okay. What'd you get? Is it 22.2? Okay, so then you need the total. Because see how mole fraction is the moles of that substance divided by the total. So how are we going to get the total? Got to add them up, right? So add them up for us. It looks like it's going to be 22.229, right? Okay, so now we're going to take this and we're going to divide it by that. And okay, so do that on your calculator, Joseph, because I got 1.314 times 10 to the negative third, or 0.001314. And Elisha said I was wrong. Am I wrong?
Yeah, it's 0.00130046.
I knew that, Elisha. He was going to be right. See, I think I wrote the answer to one problem. Whoops. To the wrong problem down. Because I was looking at different problems. I was like, oh, that's a good one. I'll show them that one. And I think this is the other answer. Okay, tell me the right answer.
0.00130046.
001346.
Yes.
46.
046.
046. So I did do the right thing. I just wrote it down wrong. Where it was where you said it's a 0, I wrote a 1. You see that? Okay. Notice this has no units. It's a ratio. Okay. No units for this because it's moles divided by moles. Moles cancel out. If you have the same thing in the numerator and denominator, you get to mark them out. All right, you learned some college chemistry. Is that all right? Wasn't hard, was it? We'll put a little box around our unit, our things. Make it prettier. Okay, let me fix it on here. While I'm here, so I don't do it again. So what I did wrong is that should be a 0. And that should be a 0. Okay, there's zeros now. Next, page 3, moving on right along. Okay, so more about solutions. Aqueous, or most of what we study, what's aqueous in? Water. Sounds like the Spanish word for water a little bit. So how it works is these ions have charges, and so the negative part of water lines up with the sodium, the positive hydrogens line up with the chlorine. They're moving because of the kinetic molecular theory. They're moving, and they rip it apart. Now, why do they want to stick? Which one of our intermolecular forces is happening? And remember, we have 4 of them. Is it London dispersion? No. Is it dipole-dipole? No. Is it hydrogen bonds? No. So it's the other one. Anybody remember the other one? Ion dipole. Good job. Remembering the other one, the one we don't talk about so much. Okay, next. So I think these look like little Mickey Mouses. That's why it's Mickey Mouse attacks. Okay, when ionic solids dissolve, they become, and I got all excited, and it's just ions in solution and can conduct electricity. So salt water conducts electricity, the non-electrolyte sugar doesn't. So a strong electrolyte dissolves completely and conducts really good. So example is Gatorade, and that's why the Gatorade logo has a lightning bolt on it. Gatorade conducts electricity. Okay, so it's called an electrolyte. You need that word. Okay, so ionic form. This is another new thing for AP. All that was review except the mole fractions, right? Except this. Okay, so when writing chemical equations, you can write strong. So if they actually dissolve, ionic compounds in ionic form. So instead of writing in our balanced chemical equation this, you write this. You go ahead and write it as an ion. So you put that as an ion, because this is if they are dissolved, if they're being dissolved in water. If this is aqueous, we can write it like that. Okay, not all ionic compounds dissolve in water. We're going to memorize the rules about this later. So I showed them to you in honors. It was the little pig saying NAGSAG, Castro Bear, PMS. But that's okay if you don't remember it, because we'll go over it again. Okay, acids and bases dissolve in water too and can also be written in ionic form. But only the strong ones that dissolve completely. Like hydrochloric acid, it dissolves, so it dissolves into H plus and Cl minus. That's a strong acid. Barium hydroxide is the base. So barium plus 2 plus the hydroxide ion, and I've got 2 of them. Okay. Now, you're eventually, well, I'll say this first. When acids and bases dissociate completely, they are called strong, and they're also strong electrolytes. We'll learn more about this in Unit 8. And in Unit 8, you will have to memorize the strong acids and the strong bases. Now, I was watching a video of another AP chemistry teacher, and he said, you should go ahead and memorize them now. So, over here is a little thing that another AP student made last year. At the end, after we take the test, y'all will be allowed to do a project to drop a test grade. And this is what she did. She made these little posters of the mnemonic devices to memorize the strong acids and the strong bases. So she did. So I brought no clean clothes, and Lily and Nate robbed a bank and kept a crispy spark of cash. So if you want to go ahead and start memorizing them, they're right there on the wall. Or you can wait till Unit 8. But before the AP test, you got to memorize which ones are the strong acids and the strong bases. All right, on to our next page. Okay, molecular compounds. Most molecular compounds are non-electrolytes and do not conduct electricity. Example, sugar. And we did a lab in honors where we did sugar in water and salt in water, and the salt in water conducted electricity, and our little conductivity testers lit up, and the sugar didn't. In Corn's class, did y'all do that lab? You think you did? Good. All right, good. Okay. So separation of solutions and mixtures. There are different ways of separating mixtures in chemistry. And we already talked about the second one, chromatography. We did a lab with it. But I wanted to show you distillation. It's important. When I was in AP chemistry in high school, we did a distillation lab. But I went to a school in Cobb County that had a lot of money. And this is very expensive equipment. And we had enough for every lab group to have one. And I've got one of these, and it doesn't even work good. So I might drag it out and show it to y'all. But I don't think we're doing a lab with it because it'd be kind of boring for us all to try to share the same piece of equipment. So this is how it works. You put a mixture of 2 chemicals in here. The chemicals have different boiling points. You heat it up, and the one that has the lowest boiling point will come off first, will become a vapor first. Then you've got a thermometer in here so you can regulate the temperature so it doesn't get too hot too fast. And then the vapors come in here, and you've got in this little middle tube, and then you've got these hooked up to your sink, and cold water from the sink is coming in here and going out there. So it's flushing this with cold water, and it makes it go back to the liquid form, and it drips over here. So this is how they purify alcohol. They start off with their alcohol all mixed in with whatever was fermenting, and then they distill it. You've heard of distilleries. And back in Prohibition here in Georgia, we had a lot of people in the mountains that were moonshiners making corn liquor. They were making liquor out of corn mash, fermented corn, and then they would make it illegally and then sell it. They did not use equipment that looked like this. For their condensation, they used copper pipe. So as the vapors went through the copper pipe, they would cool and make the liquor. Now it's dangerous because if you have bad stuff, bacteria growing over here, and you heat it up too fast, you can blow your bacteria and your poisons over here. And so that's why people would sometimes die from drinking bad moonshine or go blind. So beware the bad moonshine from the North Georgia hills. I know somebody who, he was an old man when I was a kid, and he had been a bootlegger, and he would make it in the mountains. They would always make it near water so they could cool the vapors. And then he would take it by boat to Atlanta. Atlanta was the place where they would buy it. And he got caught. he got caught, but he talked his way out of it. And he was pretty proud of that. The rest of his life, he didn't do it anymore, but he was pretty proud that he had talked his way out of getting caught by the revenuers. All right. So we can separate things that have different boiling points, and it's caused by different intermolecular forces. We already learned about that, about how that we can tell the different boiling point, how it goes because of the different intermolecular forces. That was earlier in the notes. Okay, so the one we have already done is chromatography. We did paper chromatography, where it sucked up the paper. So the things you're separating pass through a column or paper at different speeds. And it can be caused by different densities or the intermolecular forces. Okay. So my son Nathan, who works at Tech, they do column chromatography. So they pour their chemicals in here at the top, and then it goes out different speeds down into their beaker. So they use that to separate it, and then they go test it and see if they made what they thought they made in the lab. Like they're making brand new chemicals that have never been made before. Okay, solubility, more about solubility. So this is going back to Honors Review. In general, like dissolves like. Now you cannot write that as a reason on an AP test. That helps you remember, but you have to know why. Why does polar dissolve polar? Because of the attractive forces. The dipole forces. You can't just say like dissolves like. So polar dissolves polar, like water and water-based markers. Nonpolar dissolves nonpolar, like Sharpie. You can get Sharpie off and goof off. They're both nonpolar. So another word we need to know for this is precipitate. That is, in general, in chemistry class, a solid forming in a liquid. But on the weather, they talk about snow and rain being a precipitate because that's a different phase forming in a gas also. But in chemistry, it's usually a solid forming a liquid. Now, so let's look at some things here. Which of these would dissolve in water? Okay, so water, is it polar or nonpolar? Polar. Carbon tetrachloride, is that polar or nonpolar? Is this going to dissolve in water? No, it's nonpolar. How about sodium chloride, salt? Yes, because it's an ion, it's got charges. I showed you Mickey Mouse attacks. Okay, how about C2H4? That's ethene. Would it? No, that's nonpolar. Hydrocarbons like that are nonpolar. It's not going to happen. HCl, hydrochloric acid. Yes, it's very polar, isn't it? That hydrogen doesn't get the shared pair. It's going to break up in water. How about ammonia? Yes, I saw a nod yes. Why?